Welcome everybody for our last day of PyData Eindhoven 2020. This last day, or Friday, we kick off with a very amazing speaker, Adam from NVIDIA. He has prior experience in self-driving cars and also with the UK government. And he now has a very interesting job at NVIDIA. And he'll tell us more about the RAPIDS package. Actually, I had the luxury of discussing the talk beforehand with him, and we had such a lot of interesting topics that we could be presenting about, and this one was my personal favorite. Adam, the floor is all yours.
So yes, thank you kindly for the kind introduction. So today I'll be talking about RAPIDS. RAPIDS is effectively a set of libraries that provide seamless GPU acceleration for traditional data science pipeline. So hopefully you'll find it interesting. It's quite impactful, as you'll see, because of the order of magnitude of acceleration it provides. My name is Adam. I'm a senior deep learning scientist at NVIDIA, and in a nutshell, I'm an applied mathematician, and I help companies build and deploy machine learning-based products. Over the last 5 years, I've been focusing predominantly on neural networks, but still working with more classical algorithms as well. A quick agenda. So today we'll talk about RAPIDS, and in particular, we'll try to dive slightly deeper into the libraries built RAPIDS, namely cuDF, cuML, cuGraph, cuXFilter, and hopefully by the end of the talk, I'll show you how you can take your existing code today and with just a couple of lines of code change, migrated to RAPIDS. But let's dive into that a bit deeper later. So, as I've mentioned, RAPIDS is just a set of open source libraries which give you the option, the freedom to execute your entire data science pipeline from data loading through machine learning and visualization entirely on the GPU.
Adam.
Yes? I'm not sharing the screen, am I?
No.
Of course I'm not. Sorry, you didn't miss much, just my face on a slide. How about now?
Perfect.
Okay, so here we go. So that's the slide that you've missed, and the one with the agenda. So RAPIDS is a set of open source libraries that allow you to execute end-to-end pipeline. So from the data loading through any form of augmentation, feature extraction, through machine learning up to analytics entirely on the GPU. And when we've been designing RAPIDS, we were quite aware that what we shouldn't do is to build yet another ecosystem of utilities. As there exists a very well-established set of tools within this data science space. And what we wanted to achieve is to create something that will GPU accelerate them, not necessarily create yet another utility that data scientists have to use. As a consequence, wherever possible, our ambition was to maintain the API that those existing, very well-established libraries introduce. So libraries such as Pandas, SciKit Learn, NetworkX, Matplotlib, Plotly, or whenever possible, integrate with other well-established utilities such as PyTorch, MX, and TensorFlow. Also, we were aware that it's not really possible to build this library based just on a single GPU. That is why we have chosen to use Dask as a mechanism for distribution. So what we'll be discussing today are the following libraries. cuDF, which is a drop-in replacement of Pandas. By drop-in replacement, again, I mean we were trying to maintain the API so that you don't have to change your code. cuML, which is intending to be a drop-in replacement of SciKit Learn and XGBoost. cuGraph, which is intended to be a drop-in replacement of NetworkX. And we were working hard on integration with other utilities such as PyTorch, MX, and TensorFlow, as well as create a GPU-accelerated visualization toolkits, and I'll discuss some of them, such as cuXFilter throughout the talk as well. This is not the entirety of the tools that RAPIDS is providing, but I'll focus predominantly on those today. There are also other utilities. Some of them I'll mention very briefly, like QSpatial for spatial data, or QSignal for signal processing, time series data. But if you're interested in those, reach out to me after the talk on LinkedIn, and I'm happy to give you information about them and get you going. Okay, so our goal, as I mentioned earlier, was to create sane, wherever possible, or at least very familiar Python API that allows you to migrate your existing CPU-based code with either no or very low code change to be entirely executed on a GPU. And largely we have achieved it. A very large proportion of code can be migrated into RAPIDS with just the change of the import statement. So you effectively, whenever you do import Pandas, you would change that to QDF and your code largely will work. Obviously, those libraries are very mature, so we don't integrate the entirety of their API, but I'll show you how flexible RAPIDS is and how easily it is to move between RAPIDS and Pandas. So you'll see that that has very little impact, if any at all. Okay, so in today's talk, I'll focus on the key components of RAPIDS, not all of them. QDF, so GPU accelerated data preparation and feature engineering library. Yes, effectively a drop-in replacement for Pandas. QML, GPU accelerated machine learning library, including XGBoost and quite a wide range of other utilities. We'll go through the detailed list in a second. QGraph, a GPU accelerated graph analytics library, QXFilter, a web data visualization library, so effectively GPU accelerated cross-filter, and a couple others. So we'll at least mention QSpatial, QSignal, and QStreams. There are a couple of components that make RAPIDS behind the scenes. As a data scientist, you typically don't have to care about them, but it's good to know that they exist. So RAPIDS is built entirely upon Apache Arrow data representation format. Yes. It's a columnar data layout, so whenever you use RAPIDS, your data will be stored in a columnar fashion. Yes. And its emphasis is on minimizing data movement whenever possible. As you might be aware, data movement is one of the most expensive parts when dealing with GPU compute. There is so much computational power that typically the data movement becomes your major bottleneck. That's why it was very important for us to optimize that process. So we have chosen Apache Arrow because A, it's very broadly used, and we'll see it in the next slide, how deep integration with other utilities it allowed us to create. And it really handles memory with a lot of care. In a majority of cases, we can move the data between different processes, even between different programs with zero copy or at most a very shallow copy of data to minimize the overheads related. We've maintained consistency with the CPU version, and this allows us this seamless integration between tools, and this is the foundation for that seamless integration also with Pandas. SciKit Learn so that you can have parts of your code written in a classical way and parts of your code executed with no problem. By choosing Apache Arrow, we've managed to almost for free obtain integration with a very broad ecosystem of other utilities. Pandas, and you'll see how seamless it is in a second. Spark, Parquet, Cassandra, Kudu, HBase, and a very broad range of other utilities already take advantage of Apache Arrow, and this allows us to minimize the overheads related to unnecessary serialization and deserialization, as well as data movement. For GPU accelerated libraries, we typically don't even have to copy the data, we can just pass the pointer to it, passing on the computation. And GPUs are also so fast, and we'll discuss how significantly faster than their CPU implementation they are, that in fact we have to also look at other bottlenecks in the execution process, namely networking. And by networking, I don't necessarily mean the networking connecting computers in your data center, because a lot of users might not be executing in a data center at all and might not have jobs which are large enough, but also networking within the node. That is why RAPIDS is also tightly integrated with OpenUCX that allows us to use a very broad range of technologies to allow exchange of data between the GPUs. We are aware that a lot of problems will be larger than the memory footprint of a single GPU, and with OpenUCX, we can build very large GPU systems that from the perspective of a user behave as one extremely large GPU. And this is achieved because UCX not only supports basic protocols like TCP, but also can support InfiniBand and shared memory technology. So it supports a technology that we've introduced called GPU Direct RDMA, where GPUs can exchange memory between each other, not bothering the CPU and talking to each other directly. And this itself has a fairly dramatic impact. So what we are seeing here is not a comparison of code executed on CPU versus a GPU, but a code executed on a GPU, on GPUs, several GPUs with TCP as a backbone for communication and UCX. And as you can see, we see orders of magnitude of acceleration on top of what the GPU is providing. So effectively, RAPIDS has two major scaling components. It allows you to scale up. So it allows you to scale up your existing PyData code by just running RAPIDS on an accelerator, which is dramatically faster than what the modern CPUs have to offer for this workload. But it also allows you to scale out because we've built it entirely with Dask in mind, and all of the operations that are available on a single GPU can also, in a fairly transparent way, be executed across really a very large number of GPUs by taking advantage of RAPIDS, Dask with OpenUCX integration. Okay, so let's dive into its individual components. And let's do it in, say, chronological order, starting with CUDA DataFrame. So CUDA DataFrame, QDF, provides you access to GPU-accelerated ETL utilities. And for those of you that ever tried do feature engineering, you'll know that it just takes time, especially when your data sets get larger and you need to properly validate the impact your code has on the end-to-end pipeline. You'll know that the ETL process can very frequently dominate your day. Yes. So rather than spending time on things that matter, so building new features and making changes to your models, you spend time waiting for the results of the ETL, even if you have a quite substantial amount of computational resources. So we've spent a lot of time building QDF to try to alleviate that, accelerate it to the best of our ability. This is not a library that was built from scratch. It's built on top of a very solid foundation. So CUDA is a library which is more than a decade old, which is a backbone for compute on the GPU. CUDA DataFrame is built with CUDA libraries, and it primarily is built using C++ and exposed via Cython to you as a Python API. Currently, there are two main libraries that you should care about, CUDA DataFrame and Dask CUDA DataFrame, if you want to distribute that data frame across multiple GPUs. So with some vocabulary, so throughout this talk, I'll be predominantly referring to QDF, and QDF is a Python library for manipulating GPU data frames, and it's built on top of libqdf, which is the C++-based counterpart that directly accesses CUDA, but you very rarely need to care about it unless you want to extend QDF, which hopefully you won't have to. But how to use it? It's fairly simple. So what you're seeing here are two snippets of code, one written in Pandas and one written in QDF. As you can see, they are not that interesting because they are largely identical. The only thing we have changed, we've changed the import statement, and we've obviously changed the reference to the library, which we didn't have to do if we would import the Pandas in a slightly different way, but here you go. What has changed is the execution speed. Yes, if you will pay attention to the numbers, by making this small change and obviously equipping your system with a GPU, you've suddenly accelerated just the loading process by 16 times. Yes, and this is loading of a 2 GB CSV file. And you will see even potentially higher accelerations when dealing with data in a columnar format, because by definition, no conversion will be required. We're also working very hard, and that will come up very shortly, on a technology called GPU direct storage. And the GPU direct storage will allow us to totally ignore the CPU when reading the files from your disk and just pull them directly from the disk. So the GPU, after obviously getting a blessing from the operating system, will fetch the files from the disks, hopefully on the same PCI Express bus directly, without requiring the CPU intervention, which is big because when you want to load the data fast, the CPU can actually be quite busy as a consequence of reading files. So you're freeing all of those CPU resources to do something else, and you dramatically shortcut the access to the data. So stay tuned for that. That should be coming out quite soon. Early versions are already available. What to expect from QDF in terms of the speed of execution? It will vary depending, first of all, on how much data are you processing. And GPUs, if you never work with them, are to some extent counterintuitive, because the more data you give them, the more performant they get. They are so-called single instruction multiple data devices. So they feel very comfortable when the volume of data is large. So what I'm presenting here is speed when executing 3 different data operations on a 10 million row dataset in blue and a 100 million row dataset. And the unit here is not the execution time, but it's acceleration with respect to the state-of-the-art CPU. So typically this merge operation on 10 million rows will be about 500 times faster than its Pandas equivalent on a fairly decent server-based CPU. But when we increase the data size by tenfold, it will be about 1,000 times faster than its counterpart executed on a CPU. The mileage will vary depending on the operation. In a good heuristic, the more work you give to the GPU, the more performant it will be with comparison to the CPU. If you bottlenecked on something else, then you'll see less acceleration, but still even for less optimal operations, you'll see a couple hundred times acceleration. So this is not percentage, this is speed up. So this is 360 times faster, not 3.6 times faster. And we're comparing here a single Volta GPU to a single Intel Xeon CPU with 2.4. But bear in mind, QDF is still quite young. Right now, we're at release 0.16. So you should expect further acceleration. So what this slide shows you is the progress that we've made between versions 0.10 and 0.13. You can see that for merge, we've moved from 870x speedup to 970x speedup. For group by from 150x speedup to 290 speedup, and there is still much more work that we need to do. So you should expect further improvements in rapid performance on exactly the same hardware. Let's show you a couple examples. For those of you that know Pandas, they will be hopefully boring. That was our intention, to not create another learning curve. Those are just 4 different ways to create a QDF data frame. This is an example of how to create a CUDA data frame just as is from the data loaded directly from the code. This is an example of how to create a similar data frame but with 3 columns or at 1. This is an example of how to create it by reading a CSV file. And this is an example, and I'll focus here for a second, of how to seamlessly migrate the data to and from existing CPU-based libraries. So in this example, we load the data into Pandas for reasons that might be important to you. Maybe you might not be able to change this line of code for some reasons. And in this line, we just execute from Pandas, migrating all of that data to the GPU. And from this point on, you can continue executing in a GPU. Similarly, as you can imagine, apart from pandas, we have a routine called toPandas, through which you can return the execution to your existing pipeline. So even if you don't want to migrate the entirety of your code, and that might be you might have valid reasons for that. Typically, what we do is we profile the code, we focus on the first couple of lines that have the biggest impact on the execution time, and we migrate only those. We validate, and we do it again. That way we can create the biggest impact. And let's change. Oh, here we go. Again, couple more examples, this time working with the GPU data frame. And again, hopefully you'll find them very familiar. This is just a head command that will show you the first 3 rows of the data. Again, identical syntax. This is a command for finding mean and standard deviation of a column. Again, identical syntax to what you would expect. And this is an example of map with a custom function. And again, it's an identical syntax. This is a row slicing function. Again, identical syntax to what you would expect. Then this is a function to count the values and find the unique values in a particular column, and an example of how to change the data. So the reason I'm showing you those examples is to once again stress that wherever possible, we've been trying to not change the syntax. And if you organize your code in a correct way, in the sense that you have you don't refer to pandas directly, but you just centralize it in the import statement, you might be able to change your entire code with just a change of the input. Again, examples of query, sort, group, and join operations. So again, query syntax identical to what you might expect. Similarly, sorting, one-hot encoding, aggregating data, and joining the data has identical syntax to what you would expect from your existing library. So please consider using QDF. It will save you a lot of time. Even the most trivial operations will execute substantially faster than your existing code, and you'll be able to focus on something else. Let's move now to QML. QML is effectively a library that is supposed to achieve the same, but for your machine learning part of the pipeline. So it's supposed to be a drop-in replacement for utilities such as SciKit Learn and XGBoost. Again, the way it's designed, it's very similar. It's not built from scratch. It's built on top of a very well-established libraries. So CUDA and a wider set of CUDA libraries such as FastCap, QSolver, and vgraph. A lot of those libraries used for decades in the scientific community. We didn't want to build it directly on top of those libraries. Instead, we've created another library that you might find very interesting called QML prims, where majority of the code resides. Bear in mind, when we've been migrating machine learning libraries is much more difficult than migrating the data loading libraries, in the sense that a lot of algorithms in this space are not inherently parallel. So in a lot of cases, we had to reinvent their implementation. So hopefully you'll find those primitives quite useful if you want to build some more complex functionality that goes beyond the existing machine learning utilities, existing machine learning algorithms. On top of that, we've created a C++ based library called QML algorithms that captures all of the algorithms that we are supporting. And that is exposed via Cython to you as a QDF, QML interface, and Dask QML interface for distributed execution. As of September 2020, version 0.15, and I think just literally days ago, 0.16 was released, but this is largely the same. Those were the key algorithms that we've supported, plus XGBoost, but I'll focus on XGBoost separately. So how to read this table? We don't have the same implementation across all of the algorithms quite yet. So all of the algorithms listed here have a single GPU implementation, meaning that your data plus any intermittent structures need to fit within the memory of a single GPU. a large proportion of algorithms has a multi-GPU implementation, meaning that if you have, say, 4 GPUs in your desktop, or 8 GPUs in your server, or 16 GPUs in your server, that algorithm will execute across all of the GPUs within that server. And it will do it seamlessly, so you don't have to really care about it all that much. And also a subset of them has multi-node and multi-GPU implementation. And that means that if you have, say, 2 servers, and obviously if they have enough network between them, then those algorithms will execute on all of the GPUs within that cluster. So if you have, say, 32 GPUs across 2 servers, those algorithms will automatically take advantage of all of them. By the end of this year, we're hoping to not necessarily increase the number of algorithms unless we hear from you that that is really needed. And we're really responding to your feature requests on Git. So if you're working with Rapids, that's the best way of communicating with us. We always have someone watching there. So by the end of this year, we're not necessarily planning to extend the list of the GPUs, but try to focus on filling the gaps in this table. So more and more algorithms will gain multi-GPU and multi-node support. Especially multi-GPU is important. A lot of users with problems that are just bigger than 32, 40 gigabytes that you'll find in a single. Again, in terms of syntax, it should be fairly familiar. So what you're seeing here is a SciKit Learn, PCA implementation versus QML-based implementation. To simplify and to focus on QML, we've left the data loading parts the same. So we load in both cases using classical utilities, Pandas. We need to add additional line of code to move the data from Pandas into CUDA DataFrame. And then the syntax is for PCA is identical. And so we fit transform X. What is not identical is the execution time, because on a fairly modern server-based CPU, so Intel Xeon E5-2686, this snippet of code would take about a minute, so 57 seconds. On a GPU, this snippet of code will take you about 4 seconds, 4.28 seconds. So a fairly dramatic acceleration, and that acceleration spawns beyond just principal component analysis. What you're seeing here is a comparison of a single GPU, so Volta V100, to 2 20-core CPUs. We have 2 tables here because there are some, those algorithms are quite lightweight and have low memory footprint, so we can fit very large data frames with them. So this is a comparison of 1 million, 2 million, and 4 million row operation. Where 4 million row operation is not present, that means that it didn't fit in the memory of that single GPU. This is a 16 gigabyte variant, by the way. So again, the units is the speed up over those 2 20-core CPUs. So this single GPU will be about 120 times faster than those 2 20-core CPUs. For linear regression, about 69 times faster than those 2 20-core CPUs, then 46, 22, 12, 6, 5. So the mileage will vary depending on what you're executing. The acceleration will be dramatically higher for algorithms that are computationally heavy. So as you can see, the more computationally heavy algorithm, the higher acceleration. And in this case, we achieve 730x speed up. So this is not percent. This is 700 times faster than its CPU counterpart. XGBoost is a very important algorithm right now for the community. It seems to be the tool of choice for a very broad range of problems. So we, from day one, had an XGBoost implementation in Rapids. In fact, that implementation is available in XGBoost. So even if you don't want to use Rapids, even if you use exclusively XGBoost, that code is there for you to use. You just have to change one flag. And it's tuned for extreme performance. So what you're seeing is a comparison of a single server here with 16 GPUs to 100 CPU servers. And that single server will be about 10 times faster, roughly, than those 100 CPU servers. So if you consider using it, you'll save yourself a lot of time. And again, that's not something that is finished. There are still more work to be done. We're working on a very broad range of optimizations. So what you're seeing here is a comparison of RAPIDS 0.2 and 0.10, and the differences in speeds are quite substantial. We also are aware that machine learning is not exclusively training, but it's also inference. So we're also supporting a forest inference library that you can use to deploy those trained models to production. And again, those will be about an order of magnitude faster than the CPU counterpart. And so this means that you can buy 20 times less servers to serve your model, or 30 times less servers to serve your model. So not a trivial improvement. A similar story is for cuGraph. I will not go into the details, but again, we're not building from scratch. We're building on a known foundations. You can fit very large graphs on GPUs. So on a single GPU with 32 gigs of memory, 500 million edges, no problem. On multi-GPU, billions of edges. And let me know.
Adam, we need to keep the time in mind a bit. And
Yep.
we do want to do two questions from the audience, if that's okay with you.
Yep.
So they are
Sure.
both related to Pandas. So you mentioned there's a 90% of the Pandas functionality are already in.
Yep.
So what things are still not in? So what Pandas functionalities you haven't had yet?
A lot of stuff is not in. So those are all very large libraries, and we are not planning to just rewrite all of them from day one. We're following the request from our customers. We have a very simple approach. We're observing the Git repository. We're working with a very large number of Lighthouse account users, and we're accelerating them one by one. If something is not there, please reach out on Git, describe why is it important, and our team will pick it up. Hopefully within a couple of sprints, they'll be able to add it. I don't have an exact list. There's a lot of stuff is implemented, but a lot of stuff is not.
And then the second question, are you aware of any Pandas functionalities that you'll probably never take into the package?
No, I don't think so. We don't think like that. We don't know what is needed and what is not needed. You need to tell us. We are not all knowing. Yeah.
Yeah, so whatever is needed, you'll fix, basically.
Yeah, because effectively, we don't know what the entire world is doing. So we're really responding to feature requests. If we get a feature request that is well motivated and we can understand why people need it, we typically put it into a sprint to solve it.
Okay. Cool. Well, thanks for the amazing talk. Let's switch to the Discord channel. If you can please share also the links to the tutorials. Sure. I think they will be very interesting. And I think we have a couple of other questions that we can discuss in the Discord channel.
Yep. Okay.
So thank you very much.